All right, this is where we left off last time. We had just finished talking about all the quantum numbers and what they mean, which I'm sure you've absorbed fully and are happy to move on. Now, these are the orbital shapes, of course, the S, P, D, and F. Okay, the sphere, the peanut, the cloverleaf, and the more complicated cloverleaf. Now, how do we know where the electrons go? Okay, well, just like pouring marbles in a jar, okay, you start at the bottom and you fill toward the top. Okay? And the lower energy level is what gets filled first. So you start at the lowest energy level, the lowest orbital in that energy level. Then you go up to the next energy level and you start filling from there. Okay? And knowing which orbitals and which energy levels to fill can be complicated because a higher orbital, or a higher sublevel, excuse me, in a lower energy level can be at a higher energy than a lower sublevel of a higher energy level. So just to make that a little bit less confusing, say you have energy level 3, S, P, D, and then here you have energy level 4, S, and then P, and so on. Okay. And so the way these things are split up, you do end up with, the higher sublevel here. This would be level 3D, being at a higher energy level than 4S. Okay. So it is possible, and happens quite frequently, that you're going to have to bounce back and forth between these things. Now, there are a couple of ways to keep that in mind. One is to memorize a chart like this. I do not recommend it, but it would be possible. So you can see, looking at this chart, you start off with 1S, then 2S, then 2P, then 3S, then 3P, then 4S, then 3D, then 4P, 5S, 4D, 5P, 4F, 5D, 6S. I think next would be 5F actually, then 5D. This chart is confusing and wrong, so you definitely don't want to memorize this chart. But there are rules. The simple rule is known as Aufbau. It's German. It means construction. The rule for how you construct the in plus L. Okay. Basically, you can add in and L together, and your electron is going to go in the lowest available orbital that has that n plus L. Okay, so for n equals 1, L equals 0, that's the 1s orbital, n plus L equals 1. Then 2 plus 0, the 2s orbital is 2. Okay, remember, if L equals 0, you're looking at an s orbital. Now when L equals 1, that's a p orbital, so 2 and 1, 2p. N plus L equals 3. Then 3 and 0, the 3s orbital, n plus L equals 3. And that's the first time you have a place where n plus L are equal to each other, with a different energy level and different L. Okay, so you always go to the lower energy level first. So 2p and 3s, the Aufbau is equal to 3, but you go to 2p before you go to 3s. Now 3p has an Aufbau of 4. 3D has an Aufbau of 5. 4S has an Aufbau of 4. Okay? So 4S comes before 3D. Then you're going to have 4P with an Aufbau of 5. That's the same but 3 comes before 4. Then 4D has an Aufbau of 6. Then 4F, 1, 2, 3. 4F has an Aufbau of 7, and so on. But that is still fairly complicated. You can work your way through it. You can make this table over and over again. No problem. It would be super easy, but it would get fairly tedious. So we have this chart here in the upper right-hand corner that makes it a little bit simpler. You're just drawing these diagonal lines over and over again. So 1s, then 2s, then 2p before 3s, 3p before 4s. Okay. Then after 4s, you'd have 3d, then 4p, then 5s, then 4d, then 5p, then 6s, then 4f, 5d, 6p, 7s, 5f, 6d, 7p. So if you're a more visual learner in that way, that would work just as well. They cut it off at 7 because we've not found enough elements to need to go below the 7th row of the periodic table. Okay, remember, the energy levels here correspond to rows in the periodic table. Speaking of the... I forgot how complicated some of these slides are. Okay, yes, that rule is kind of complicated. But speaking of the periodic table, this makes it even easier. You don't need to memorize those things. You just need to look at the periodic table. And you follow the periodic table, element by element, and it actually tells you which row, or which N, which L, and which electron even, if you want to think of it that way. It tells you which orbitals you're in. Level, sublevel, and orbital. So hydrogen here is the first electron. It goes in 1s. The second electron, you jump over here to the other side of the periodic table for helium. That's also 1s. Now, the s orbital, it's a single orbital in that sublevel, I should say, in the s sublevel. So it's all by itself. It can only hold 2 electrons. So you have to jump to the next energy level because the first level has 1 sublevel. Now, the second sublevel has 2 sublevels, the s sublevel and the p sublevel. So our first one goes in 2s. Our second electron goes in 2s. Now the s sublevel is full. It only has 1 orbital. So we come over here to the p sublevel. It has 3 orbitals, so it can hold more electrons. And that's why this part of the periodic table is 6 columns wide, 6 groups. So 2p1, 2, 3, 4, 5, and 6. Now that p sublevel is full. The second energy level only has 2 sublevels, so the second energy level is full, and we hop down here to the third row. 3s, 1, 2 electrons. Now the s sublevel is full. We hop over to 3p. The p sublevel can hold 6 electrons, and it's full. Now, because of Aufbau, we know that 3d doesn't come next. Next is 4s. You hop down here, 4s, and now 3d can hold 10 electrons because there are 5 d orbitals. That's why it is wider than p, because there are 10 elements, 10 groups, 10 columns in this portion of the periodic table. So after you fill in all those d electrons, you're back to the 4th energy level with 4p, and now the 4th energy level is full. And you hop down here to 5s, 4d, 5p, 6s, and this is where it might trick you, because you'd hop down here to the 4f. We had to pull these 2 rows out of the periodic table to keep it from being absurdly long. 4f is sandwiched in between 6s and 5d. And so 6s, 5d, 6p, 7s, 5f, 6d, 7p. We have made, I believe, all the way up to this last element here in this last row in nuclear reactors. But everything after uranium, element 92, down here in 5F, is artificial. And most of the stuff after plutonium, I think it is, only has a half-life of a very small fraction of a second. So most of 5F, most of 6D, and all of 7P, I'm certain of 7P, doesn't really matter for chemistry. It barely, well, nuclear physicists might think they're super important for reasons, but we don't care too much about them. But so long as you have a periodic table handy, and for my tests, you always will, and if you have access to the internet or any chemistry textbook, you always will, then you can always figure out how to fill your orbitals and energy levels. Because the periodic table has the shape it does because of those energy levels. That is one of the more astonishing things about quantum mechanics. The periodic table was developed long before we even really knew about subatomic particles. It was the Russian Dmitry Mendeleev. You don't need to remember his name, really. Mendeleev. He just looked at the elements, and he saw the repeating patterns of their behaviors, their chemical behaviors, their chemical properties, and he laid them out in this pattern. He wasn't the first one to notice the pattern, but he was the first one to move beyond the second row, or the third row, I think it was, and recognize that there was a change in the pattern and so on. He made predictions, like he predicted the existence of germanium, and he swapped, I think, iodine and its neighbor. So he did a pretty good job with this. He came up with, obviously he only came up with, the first few rows. They didn't have these guys down here, definitely. But the shape of the periodic table, it had this odd shape even before they knew about sublevel orbital spin. So they were able to see this even before they knew why. But with quantum mechanics and the really weird math that you can do with wave equations, we finally understand where this shape comes from. We'll get a bit more into the chemical properties and why those are the results of this thing right here in a bit. But first, I want to give you a little bit more of a way to write the electrons. And that means we're going to be talking about electron configurations. Electron configuration means that you actually write down what electrons the element has, or atom. You can talk about individual atoms in this way. By writing down the energy level, the sublevel, and how many electrons are in that sublevel. Okay? So hydrogen has a single electron, and it goes in the 1s orbital. Okay? It's the single orbital in the sublevel s of the first energy level. Okay? So 1s. And there's one electron there. That's hydrogen. Then the helium atom has 2 electrons in the 1s orbital. So it's 1s2. Okay? Just written as a superscript. Okay? Then lithium has 3, 1s2, and 1 more electron in the 2s. So it's 1s2, 2s1. You skip ahead a little bit further. You have carbon. It has 2s electrons in the first energy level, 2s electrons in the second energy level, 2 p electrons in the second energy level. 1s2, 2s2, 2p2. Nitrogen, right after carbon, 1s2, 2s2, 2p3. And then coming to oxygen, the very next one, 1s2, 2s2, 2p4. Fluorine, 1s2, 2s2, 2p5. Neon, the noble gas right next to fluorine, is 1s2, 2s2, 2p6. And the second energy level is full. And then sodium comes right after neon, 1s2, 2s2, 2p6, 3s1. So those are the electron configurations for the first few elements. We're at 15 minutes. So the first thing I want to point out is Hund's rule. Hund, probably. I think it's German for hound. You notice that when you have multiple orbitals in a single sublevel, you put the electrons in separate orbitals first. You don't pair them up unless they have to. Remember, like charges repel. Negative charges repel each other. So they go in separate orbitals, and they point in the same direction. They're all going to be spin up, or they're all going to be spin down. Which one you choose, up or down, is up to you, but they all point in the same direction. It's a thing called resonance. We'll discuss that more in Lecture 13.